ladies and gentlemen, welcome back. In the last class, I introduced you more fully to the general idea of systematicity theory. Systematicity theory is a theory which aims at explaining what the nature of science is. And I went further in presenting the general framework, the general idea of systematicity, which comprises then 9 dimensions in which it claims that science is more systematic than particularly everyday knowledge. The problem, or one of the methodological problems with systematicity theory, is that because it is a descriptive theory, it tries to describe the sciences that really exist. Because it is a descriptive theory, the justification of systematicity must refer to the real existing sciences. But, as I told you, there are many sciences. There are something between 250 and 500 disciplines. And if you look more closely, then we are encountering a number of several thousand, 8,000 perhaps, of subdisciplines. And as systematicity claims something about all disciplines and subdisciplines of science, in these 9 dimensions, we have to argue quite a lot in order to justify systematicity theory. This is a methodological problem that cannot be avoided. And the way out of this methodological problem is that I give you many examples from different areas such that you can get a feeling for the theory and for the rightness of systematicity theory by looking at many different areas of science and by showing you the mechanisms and the strategies how the sciences try to increase their systematicity. So we have to go through these 9 dimensions, and we went in the last class, we went through the descriptions. I showed you that the classical formal sciences have a systematicity in their descriptions, a very high systematicity by axiomatic descriptions. Then we have classification, which is a means applied by many different sciences. Classification systematizes your descriptions. If you have many things, then you classify them in the first step, and therefore you know then which element belongs to which class, which is of course part of a systematic description. Furthermore, I said something about quantification of descriptive statement, which immediately, if they are successful, get you higher accuracy of statements and much more order. You get many more statements, quantitative statements, about something than typically qualitative statements. You get complete order because numbers come ordered. Then I spoke about empirical generalizations, phenomenological laws. I should also say, I think I said it, but you may really take it down as a note. What I mean here as well are state equations. That is something that engineers use quite often, that you have a certain system and then you have a state equation. And a state equation just connects the variables by which you describe the system in an equation. I mean, the example I gave you is the very simple state equation of the gas, the ideal gas. But state equations are used in many different areas in which you simply, that's a way of describing a system. Namely, the description tells you what the relevant variables are in this particular case. The pressure, the volume, the number of moles, that means the amount of matter you are looking at, and the temperature, and it says these 4 are the variables by which you can describe the system meaningfully. They are interesting variables of that system, and then the equation shows you what the connection is between these. And therefore you get here, in this equation, a state equation for the ideal gas, you get the information, A, what are the relevant variables, and B, what is their connection? And that's, of course, describing the systems in question. And, of course, I'm not describing by that state equation just one particular sample of gas, but the claim is this equation describes all so-called ideal gases. These are just gases under normal laboratory circumstances. All gases obey this equation. Only when you change the pressure, so the volume or the temperature very strongly, then you get deviations from the ideal gas equation. So this is a very compact description. And if you compare that with other descriptions, say a verbal description of some gas, what it does, I mean, it's absolutely unsystematic, and you say, yes, it's very fluid and it goes through little holes and whatnot, but once you have such an equation, you've got a lot of information in an extremely systematic way, applying to a large number of systems. So you see that these empirical generalizations of state equations have an immense descriptive power systematically to describe systems. Okay, and then we have for historical disciplines and for certain developmental processes, periodization, which is similar to classification. You just you get slices of a certain historical process, and you get a pattern. And a pattern, again, of course, is something systematic, applying if it's historical processes to one historical process, but tells you, look, there are phases and they are different from each other. Just remember, when we talk about periodization, just remember paradigm theory, which gives you a very general description of the scientific process, the processes in science, by telling you, look, there is this pre-normal phase and the normal phase, and then the revolutionary phase. And that describes, of course, schematically a large number of processes, and therefore, of course, that's very systematic to describe the processes in science instead of describing every single one individually, right? It's much less systematic. So this is also a means, and if one looks more closely to historical descriptions, then you find that they have the same structure as everyday stories. When you tell your story, why and how you came to Germany, for instance, and when you compare that with the stories that professional historians tell, that one can find out that the structure of the stories is the same. Namely that you say, well, I wanted to do this, and then I did that, and then this happened, and then I had the following accident, and this happened, and so on and so forth. So you're not really, you're describing a series of events which are partly accidental, and that is something which is can be observed everywhere in historical descriptions. This series of events, partly accidental, partly intended, and the whole thing then from a certain beginning to a certain end has a certain structure. And this structure is in this historical sciences the same as in everyday stories, but it is more systematic. People are more careful, more orderly, more disciplined when they tell these stories. So if you look at this chapter, which I discussed in the last class, you see quite obviously that regarding descriptions, the sciences, in all the sciences, one can infer from here, at least have the suggestion that it's right, all the sciences are much more systematic in their descriptions than we are in other activities of everyday life descriptions. Okay, I got so far in the last session, and I come to the next section now. So, but I want to give you the opportunity to ask questions if there are any. If there are no questions, then please don't ask them. But if you have questions, go ahead. All right, so you got the joke. Thank you very much. Okay, if there are no questions indeed, then I continue. All right, so I come to the explanations. I've got to get free here first. Otherwise, I have to explain you why I fall over. Okay, I come to the explanations, and it is quite obvious that what we want to have in the sciences, of course, is explanations. There is not a single discipline, as far as I'm aware, that does not intend to give explanation. This is one of the main things, that science explains us why certain things happen, why certain processes have the form that they have, why certain things exist in the world, why certain apparatus function or don't function, and so on and so forth. So the description part is not so thrilling, but what we really want from science is, of course, explanations, and then, of course, we want to have the possibility in engineering, of course, of applications of using science in order to build something and to create an artifact with a certain function. That the explanations is a part, of course, more for the natural sciences and social science, also humanities, that you explain something, whereas the aspect of explanation of existing phenomena is less important for the engineering sciences, because there you want to put knowledge into practice. But for the sciences, the non-engineering sciences, of course, this is probably one of the most important aspects, what we expect from science. We do science in order to understand the world, roughly speaking. We have to describe it, of course, first, what's going on, and then we try to understand what is going on here and ask the question, why does this happen? Why is this so? Why do so many animals and plants exist, and so on and so forth? These are the questions that science is supposed to be answering. Now, the point is that I'm making is, in systematicity theory, is of course that also in everyday life we provide explanations for several things. They may be sometimes good, sometimes bad, sometimes in the middle range of quality. But the point of systematicity theory is that basically, very roughly, the patterns of explanations we encounter in everyday life and in science are not so dissimilar. But one point of dissimilarity is certainly that the explanations in science are more systematic. And that is what I have to argue for in this section in order to show you what systematicity theory claims and why one can be quite confident that systematicity theory is right here. So let's go to the explanations by empirical generalizations. First, I mean, these are explanations if you have, for instance, an ideal gas and you have a certain change, there, they say, in the pressure of the gas, and you don't understand why where this pressure difference comes from, and you ask, why do I have an increase of pressure? And someone tells you, look, this gas was standing next to, to some sunlight, and the sun heated it, so the temperature went up, and it was in the mass was the same, and the volume was the same. It was a tight container, and the temperature went up. Then, of course, that leads to an increase of the pressure, right? Proportional. So double temperature measured in Kelvin, and you get double pressure. So if you want to have an explanation here, these phenomenological laws or state equations also provide you with explanations if you use them properly. Say in a situation where you hadn't noticed that the temperature has changed, but you notice because you've got a measuring instrument that you notice the pressure went up, and you say, what the hell is going on here? And then someone tells you, look, this is because the temperature has changed, and therefore the pressure changes because the other variables are constant. So you can use these empirical generalizations also for explanations. They are not terribly deep. It may be that you say, well, this is nice that I know that a gas obeys this equation, but still I don't understand why does this equation hold for gases. And then you want to have a deeper explanation for something like a state equation. In engineering, very often, if you're happy with your state equation, you don't care about it. You're just happy to know it, you know it applies, and then you use it in order to create something. But if you look at the theoretical sciences, sometimes you have an interest to understand more and also to understand possibly the limitations. If you want to understand the limitations, you better have a theory to understand such an equation and not just accept it. That's also for engineering as well. If you really want to understand where an equation breaks down, for some reasons, you want to understand where does it hold and why, right? And that's the next step. You have then, for these sort of deeper explanations, you have the explanations with recourse to causal theories. Larger theories, for instance, about materials. Say you have, you want to know something about the behavior of materials, and if you want to have a deep theory for that, then you must use quantum theory. That tells you what the atoms or the molecules that the body is built up of, how they interact and what they do. And then you have a deeper theory that explains then, for instance, state equations. And you see, again, this is a measure that is extremely systematic by unifying different areas. So with quantum mechanics, I mean, even with classical mechanics, you can already explain this equation, but you can explain many other equations as well. And what you get then is a unified picture saying that, well, for certain states, this equation holds, for other states, that equation holds, and you get a unified point of view from which you can say, oh, I understand why under these circumstances this equation holds. From the same point of view, I can understand why that equation holds, and I can also understand why that equation holds. Right? A unifying theory, therefore, adds systematicity to your explanations. right? It gives you a deep level from which you can look at, for instance, state equations and their explanations and explain their explanatory power. So this is also a means of systematizing. Again, it depends both in science and engineering whether you need these deeper theories or not. Sometimes you don't need them. You're just happy with these sorts of equations if they do their job. But sometimes you want to have more. And of course, in the theoretical sciences, if you look at physics as a whole, then of course one wants to have the bigger picture by means of big theories. Right? This is important for physics, for a physics that doesn't look at primarily at applications. As an intellectual enterprise, it's important there. In other areas, it's not so important. But the point is the general tendency is that you get more and more systematicity by unifying parts of science into large theories. And that is what these large theories do. They provide you with explanations that are unifying and therefore more systematic than other explanations. Okay, in the social sciences, what we have very often there, and in the social science I include economics, which is the social science that some of you study and apply, you have very often the explanation of actions with recourse to intentions and belief. And just to make this more transparent, when, for instance, someone saw me leaving my institute today at 9:50, I think I left, and she wants to explain, why does Paul leave his institute now? Right? Then it's a very easy explanation. You must know what I intended to do. I intended to be here 10:05 in order then to start my class, right? Or prepare the computer and prepare everything to be able to start my class at 10:15. And you not only have to know that I wanted to start my class, but you have to know what I think of the situation I'm in before starting my class, of what is appropriate of realizing that goal, right? You have to know that. And if you ask me, then I would have told you, yes, I wanted to be here in E11 at 10:05 or something, and in order to do so, I have to leave my institute at about 9:50, right? Because I want to catch the tram. I know I have to wait for the tram, maximum 6 minutes. The tram takes, I think, 5 minutes or so. So I guess I got to leave my institute at about 9:50 or 9:55, and then I'll be here at 10:05, and then I can start my class at 10:15. So if you want to explain, so if you see me leaving my institute and you ask, why the hell is he doing that? It's nice and warm inside the institute. It's cold outside. He doesn't want to have a breath of fresh air. Why the hell is he doing that? Then you get an explanation with recourse to my intentions, what I want to do by doing what I do, what I want to achieve, and what my judgment of the overall situation is. I mean, pathetically speaking, what the state of the world is in which I want to realize my goal, right? And that is, for instance, I'm not using a car, I'm using the tram, and so on. It takes so long, and blah, blah, blah. And knowing what my judgment of the situation is, then you understand why I did what I did, right? This is a typical form of explanations by intentions and beliefs, right? The intentions is what I want to do, and the beliefs are about the situation in which I consider myself being in, right? I make a judgment, what is my situation, what's the situation of the world, and what is it what I have to do in order to realize my intention. And once you know that, what an actor thinks of his or her situation, and what she or he wants to do, then you can understand why the person acts as he or she does. Right? In economics, you have that in terms of preferences. Right? The main thing are the preferences in economics, and these are intentions. That is what you prefer. What good is it that you prefer to have? And then you look if someone then buys or doesn't buy, or sells or doesn't sell, that depends then on the judgment of the situation. For instance, whether you make a profit or whether you prefer this or that, and what your realization is, what your ideas, your beliefs are about a realization. And also, if you look at history, for instance, there you have also, in some parts, the explanation of actions of individual actors. So I had a closer look, for instance, how the historians deal with the question when the atomic bomb was dropped over Hiroshima. That was President Truman, the American President Truman, who decided that an atomic bomb should be dropped over Hiroshima in August 1945. And if you look, and this is, of course, has been a world-shattering event, as you know, and the historians, there are many, many books and articles about this event, and when you look at what the historians do, is that they precisely want to dig out what exactly were the intentions of President Truman, what did he want to achieve, and then why did he choose, I mean, he wanted sort of peace or conquering of the Japanese, whatever it is exactly, and then you have to know what his judgment of the overall situation was, why he thought it would be appropriate then to use atomic weapons against the Japanese in order to achieve what he wanted to achieve. Right? I'm not evaluating that, whether that was morally good or bad. That's not my point here. I'm just telling you, if you want to understand what was going on, that's a different thing than morally judging it, whether that was right or wrong. That's a different story that historians are typically very reluctant to deal with. Anyway, so if you want to understand why President Truman then gave the order to drop the atomic bomb, I think on August 6th in 1945, then you must understand what were his intentions, what is it that he wanted to achieve, and what was his judgment of the overall situation during this war and the political situation, such that he thought that dropping the atomic bomb is an appropriate means to realize his goals. So that's no difference in the structure of the explanation than the trivial thing, why did Paul move out of his institute at 9:50 and went to the tram? It's exactly the same structure of explanation. The one action is, of course, rather trivial, and the other one is a world-shattering event. But the explanation is similar. But then if you look at the accuracy and the systematicity of the explanation, then you'll find a very, very, very deep difference. Because this explanation, why I left today at 9:50, will be given only once in the whole course of the world. That was just now. I explained it to you. Right? I guess no one will ever ask me why I did that. I gave you the explanation, and I gave you an everyday explanation, right? And I gave you the necessary, it was a fine explanation. I mean, it was even true. I didn't lie to you, right? But if you compare that with these 20 or 30 books that I found just about this event of President Truman, they went through his diaries, what letters he wrote, what conversations he had, what his advisors said, and so on and so forth. It is very complicated, then, because he also changed his mind. 6 weeks before he made the decision to drop the bomb, he said only military targets are possible for the atomic weapons. And then he changed his mind, because Hiroshima was not a military target. It was a city, it was civilians that were hurt there. And therefore, it's very complicated to find out what exactly happened with his intentions. And you need books and books and books with many footnotes and new material. And if you look at that, how historians do that, of course, that's extremely more systematic than the little simple story I told you about why I left at 9:50 my institute, right? So you see here, when historians do that, and social scientists, when they try to explain individual actions, the structure is really the same. It's the same sort of recourse to intentions and beliefs about the situation. But if you look at the degree of systematicity, that's a hell of a difference, right? And again, you see here that you get, of course, a large group immediately of sciences, all the social sciences, plus then parts of historical sciences, namely the cultural history or history of human beings, not the natural history, where you find this pattern of explanation, and it's immediately then, I think, obvious that this is much more systematic than the related activity in everyday life. Okay? So, we have, and this is already, I've said something very similar already with respect to descriptions, historical descriptions, also historical explanations, where you have something so-called narrative explanations. They have the same sort of the same sort of structure than in everyday life, but are more systematic. And I guess I better give you an example here what I mean. There are, in the historical sciences, there are explanations of individual actions, right? There is an explanation for individual actions, like the example I gave you about President Truman's decision to drop the atomic bomb. But on top of that, in the historical sciences, there are also explanations that have a different form. And that is very important because the historical sciences are very different from the systematic sciences. And in these historical explanations, the explanation consists in telling a story. Right? That is very amazing. For natural scientists, usually they say, that's very funny. How can you explain something by telling a story? Right? So I give you an example that I find an interesting example. It may be a little strange and foreign for you, but you'll see immediately what I'm up to. If you look at France in the 18th century, right? Some of you may know nothing about France in the 18th century. There was a king, and the king planned almost everything, right? And the planning in France concerning the roads France is a comparatively large country, in Europe at least, in comparison to other European countries. And the planning was that the streets must be straight lines, right, across the country. And the planning was, we build streets in all over France in very straight lines. And that you find in France, when you drive in France, you find many of these old streets, they're just very straight lines from one city to the next one. Today, streets are built differently because there are too many accidents when the streets are simply straight because people fall asleep. So, you find one street, one particular street between two cities in France, and that's very amazing. That was built in the 18th century, and as I said, so you have certain cities here, and you have cities here, and the normal thing is, of course, that the streets between them, the roads, are just straight lines. But you find one here, and that goes the following way, that goes here, and then it makes a turn here, and then it goes here, right? And if you look there, you don't know why. There's not a geographical reason for that, right? So the explanation, so you ask as a historian, this is one of the streets. The street was planned by one of these French kings in the 18th century. And you say, I understand why these streets are straight and these streets are straight, the roads are straight, because that was the planning idea, and then the king just realized that, built this street and built it as a straight line, so you can understand. But you cannot understand what happens here. And in order to understand what happens here, you have to tell a historical story, and I tell you the story. The story is this, that what we don't see now is that there was a beautiful castle here by a very influential guy from France. He had a castle there, and he had excellent relations to the king. And the king wanted, of course, to tear down this castle in order to build a straight line street, right? But this man had excellent connections, and he could convince the king to change the route here. Because of his castle, he wanted to stay here, right? His wife, and with his dog, and with his slaves, and what else he had there, and he just wanted to stay there, right? And he could convince the king that the king said, okay, under these very special circumstances, I will change the route of the street, and I build the street around your little house. Your chateau, of course, your big, nice castle. And in the meantime, this castle has been demolished. It has disappeared, right? You don't see anything. But by telling you this story, right, you understand why the street makes this curve here. And what I gave you here is not some sort of regularity or something, but I told you a story, right? And many of the stories that historians tell us are not just a description. Of course, this is also a description of what happened, But it's a sort of historical, it's a story that has explanatory value. By hearing this story, you understand why the street is so irregular here. And as in history, I mean, so many things, or most of the things are irregular. You don't expect them. Everything comes different, right? Financial crisis, whatever it is. I mean, it's contrary to your explanation, to your expectations. And very often then the explanation that historians give have the form of stories. Also, by the way, in everyday life. If you tell someone why you did this and that, why you ended up being here in Germany, for instance, you meet some of your old friends and someone tells you, what happened? Why did you go to Hanover? It could have been Wageningen, or it could have been Australia to do this sort of class. And then typically you tell a story. You said what happened, right? You said, and then I got this offer. Oh, I thought it was a good offer. And then, sorry, I was not taken. I was refused. And then I took another offer and blah, blah, blah. You tell a long story. And this story then explains why you are here, right? It's not only intentions, but it's also accidents that happen, accidental stuff, interferences, things that didn't work out. You missed the plane or whatever it is, right? And all these things, different things that happen. And when you tell these stories, then you understand why a certain result occurred. And this is what historians typically do, and this is also what we do in everyday life. But the point, of course, again, it's very simple, is that if you look then at a historian describing this story, I mean, it takes 30 pages or 50 pages and many footnotes and references to plans of the king and whatnot, and all the documents finding out what sort of castle was there and why the relationship of this guy living here to the king was so good, and so on and so forth. And it's a long story and very complicated and much more systematic than a story when you explain to someone in 5 minutes why you ended up being in Hanover doing a degree in international horticulture science or water engineering, right? And it's also a story, but much less systematic than in the historical sciences typically. So you see here the same pattern again, and we go to the next mode, and I'm varying schematic here now by explanations by models. This is, of course, something which you all know by your scientific practice, be it in the engineering science or in the natural science or in economics, of course. Explanations by models and computer models, of course, very often, but also other sorts of models. Where you explain something by models, and we do similar things in everyday life as well, but we do them, of course, especially when they are mathematical models in the sciences, much more systematically. There are other uses of models to which I'm not referring. Of course, all engineers use very often real models, I mean, built really just in a certain scale, 1 to 100 or whatever it is, in order to get an impression of what a thing is and what it looks like, and possibly also some insight into functions. But that's not what I'm referring here to. But we use models. That alone, talking about models in science, can take 5 hours, no problem, if you look at different areas, what sort of models they use. So I'm not going into details here. And here's something else which you find also in many, many areas, and of course in all the areas you work in, be it biology, be it engineering, be it economics, be it social science, whatever it is, that's so-called reductionist explanations. And the reductionist explanations, they do the following. You have some sort of system, something that consists of several parts, whatever it is, be it a dam, or be it an organism, or be it an economy, or whatever it is. You always have, very, very rarely, you have absolutely simple objects. You have that in physics, an electron. An electron supposedly has no parts whatsoever. But everything else has parts and is a system, so it's a more complicated thing. And one of the explanatory strategies that is used in science very, very often is reductionist, and that means that you explain the behavior of the system by recourse to parts of the system and the laws governing their interactions, right? If you want to understand what a dam, now I talk to the engineers mainly, what a dam does when the water level increases and increases, you have, of course, look at the parts the dam is made of. namely where do the forces go by increase of the water once they reach the upper level. You simply have to know where do the forces go, and then you must understand what do the forces do at the end of the dam where it touches the mountains or whatever it is. And you have to ask yourself, how do the forces go inside the dam where you have the metal parts and the other parts, and so on. So you have to understand the behavior of this complex thing by means of the parts it is built of, right? The same is, of course, with an organism. Once you are ill, of course, the question is which parts are responsible for your illness. What is it? You've got, say, you get fever, and fever is an indicator, an overall indicator. It's the temperature, and then you look which part is it? What went wrong? So in medicine, for instance, also, of course, in other parts of biology, if medicine is a part of biology, which is not, but roughly speaking, once you look at organisms, of course, you ask about the parts. So in many of the experiments you do with the plants, which you want to make better for a certain region or more resistant to certain diseases and so on, you look at the parts you can manipulate in order to get the desired result, right? And you do it then by genetic engineering, or you do it by crossing, or whatever it is, or you change you change the environmental conditions, and you look then at the parts in order then to explain what the thing is doing. And this is a strategy you find everywhere in science. And it's very plausible. If you have something complicated, the behavior of the complicated thing will depend on the behavior of the parts. Of course it will depend on the behavior of the parts. And therefore, these so-called reductionist explanations are everywhere in science, across the board. Also in the humanities, you find that, and it's a very natural idea. Also, of course, in engineering, and if you want to design something in engineering, of course, you have an overall idea what the product should look like, but the only way of realizing the idea is assembling the thing out of parts. Right? There's no other way. If you want to build a dam, you must put the ingredients that you need for a dam together, and build the dam. And if you build a machine or whatever it is, of course, you build everything out of the parts, and you try to choose the parts and connect the parts in such a way that the behavior of the system is the behavior that you want to have, that you want to realize. It's absolutely trivial. I know that you say, yes, of course it is. But this is, if you look at it, take a step back and look at it, this is something that is then the resource for the explanation of the system, right? Also for the misbehavior of the system, the failure of the system. Of course, that's the question for the engineers. Also the question, of course, for the life sciences, where you want to understand why certain plants, for instance, don't grow the way you want them to grow, or don't get the yield you wanted them to have. And then you look, of course, at the responsible parts in order to understand what's going on and then change what you want to change. So reductionist explanations, they are not the only mode of explanations. Be very careful. Look, historical explanations are not these sort of reductionist explanations. They are different. And there are very different modes of explanation, kinds of explanation in the different sciences. But the point that systematicity theory makes, and you see that here in this long list of different forms of explanations, is that many of them you find in more rudimentary form, also in everyday life. And more rudimentary in everyday life means more systematic in the sciences. And that is the claim of systematicity theory. All right, any questions here about the explanations? I know that not everything here is familiar with you, or you are not familiar with it, but don't worry, you don't have to know all the details. I'm giving you the argument of a very far-reaching thesis, the thesis of systematicity theory, and you should have an impression of the plausibility. You don't, as I told you don't have to learn everything by heart here of these details, but what you should get is an impression of the force of the arguments for systematicity theory, because as always I try to present these theories to you as strongly as possible. Okay, no questions so far? All right, then we continue. Now predictions is something I also talked already about in the connection with inductivism and deductivism. Remember, I told you about the derivation from laws and regularities in order to gain predictions. There are other modes of predictions as well in the sciences, and here is more to it, but I'm doing it rather summarily because I can't go into too many details. So there is one mode of prediction, for instance, for solar eclipses, that we had one very recently, is by direct recourse to deterministic or probabilistic empirical generalizations or theories. And you do that in many areas, in astronomy, in nuclear physics, and whatnot. So, for instance, if I take the state equation and I want to predict how the pressure changes when I increase the temperature, then I simply use this equation, right? If I want to predict what is going to happen if I double the temperature for a gas that obeys the state equation, what happens then? And I keep the volume constant and I keep the container sealed such that no gas can evaporate, then the answer is that the prediction by this state equation is if you double the temperature, then the pressure will double, right? I simply use that. I showed that to you already in the context of deductivism and inductivism. That's the mode of explanation, of prediction by this deterministic, probabilistic, empirical generalizations. Forget for the details about probabilistic ones. Okay, that's one way. And then there are many, many ways, many different ways. Again, one could talk easily 5 hours about predictions in different sciences because there are so many different ways. Of course, the most important ones is really models. So when we talk about climate change, for instance, of course, then the discussion is always about the climate models, right? The global climate model of the Earth. And the predictions about, say, temperature increase as a dependent variable dependent on CO2 increase in the atmosphere, that's, of course, based on models. You don't have simple law for that, but you have complicated models. And then you can calculate, you can predict the temperature increase by an increase of the CO2 concentration in the atmosphere, and it's a very, very complicated model that gives you the prediction. And, for instance, models, every day you look at the weather forecast, that's done by models. Very complicated models. You need really big computers, and for the everyday weather forecast, you use millions of data points, literally millions of data points, 5 million, 8 million data points, then there are calculated data points as well, and then the computer runs for something like 6 hours, or at least this was a couple of years ago when I looked into these models. And then you get a weather prediction, and you get it on a local scale. Then by local models, they are embedded in the global models, and then you get a prediction for 3 days or 7 days, and 10 days is already not very good. But 7 days works a little, right? 3 days is fairly good. And of course, that's based on models, and you have, of course, many, many, many other things, simulations, time series, and statistics, and you use them in economics. I mean, all the economics, economic forecasting about the development of whatever it is, markets, whatever it is. In meteorology, I mentioned it. In the material sciences, you've got, of course, models and simulations by which you simulate the behavior of certain materials in order to predict their behavior. In epidemiology, and so on and so forth. It's a huge area, and if you simply look at that the models are implemented on computers, and there are sometimes a large number of equations that are then solved by certain mathematical procedures, then it's of course much more systematic than anything we do in everyday life, right? In other areas, it's quite obvious that science is here much more systematic by using all these mathematical means. And that's here what I'm summarizing. These kinds of predictions are more orderly, more explicit, and better controlled than everyday predictions. I'm not saying that they're always successful. Of course, they are not, right? In economics, it's quite obvious. They are not always, and also in weather forecasts are sometimes severely wrong. I mean, sometimes surprisingly wrong. But anyway, that's not what I'm saying, because the claim is not here to evaluate, or the aim of what systematicity theory does is not to evaluate the quality of science, but the aim is to show what is specific about science in contrast to everyday knowledge. And here we have this higher degree of systematicity with regard to predictions. Okay, I think this makes a good point here to make the break. So we have an 8-minute break, and then I continue with the remaining 5 dimensions of systematicity theory. So